All righty. Close that. So, legitimately, how many of you suffered through the hour and 7 minutes of video for today? All right. So some people watched it and suffered accordingly. So I don't know. Honestly, I kind of feel like that's punishment enough for right now, but we should have something to do today. So we can either work on some of the web work stuff, or we could work on the in-class assignment. I'm happy either way, or I can answer questions about it. The reason why I'm not, I would say the reason why I don't have a whole heck of a lot prepared is that most of that really doesn't have a lot to do with circuit analysis, or at least how we're going to be approaching things. That lecture was kind of I'm going to show you how awful it could be if we don't do the thing we're about to be doing, if that makes any sense. So it's a bunch of mathematical background. There are some homework assignments and stuff like that, or some questions here in the homework assignment about some of those topics. But with regards to how we're going to approach the circuit analysis, literally starting on Monday, we're going to throw 90% of that out the window and just use complex numbers, because it'll make our life much, much easier. So that was a terrifying amount of math. You do not need to remember how to do all of that by any stretch of the imagination to succeed in this class. Even in the further circuit analysis classes, you still don't need to know how to fumble through all that kind of stuff. That's the beauty of what's called frequency domain circuit analysis. It takes all that all those trigonometric relationships and calculus and converts it into simple algebraic relationships that look exactly like the DC circuit analysis we've done to this point, just with complex numbers. So with that being said, what do you guys want to do? Sure. So the in-class assignment, let's look through, I believe there are 4 problems on it specifically, but problems 3, you actually won't know how to do, although we can talk about it today, no problem, but you technically shouldn't know how to do until you watch part 1 of Monday's video lectures, which I think is only like 10 minutes long. It's not that bad. No, not nearly as bad. And then problem 4 is just an extension of, again, that same basic stuff. So we can go through as much as possible here. So that begs a question. Oops. I need to be sharing my screen on Zoom real quick. Share screen. I'll just share the screen. So if I switch, it'll be okay. So for problem 1 here, it has 3 parts. Parts A and B, I feel, are pretty straightforward. Part C can be extraordinarily brutal or extraordinarily difficult, depending on how we approach it. Excuse me, brutal or easy, not brutal or difficult. That would be bad, depending on how we approach it. Yeah, so it's not soul torturing or just regular torturing. It's soul torturing or easy. Sorry about that. So let's look at part A here real quick, okay? So we have f of t is equal to 300 sine 628t. And our goal is to express this function as a single cosine function, right? So we would simply apply the trigonometric identity, which allows us to switch from sine to cosine here, which that would be, let's see, 300. So sine of x is the same as cosine of x minus 90 degrees. So we would have 300 cosine 628t minus 90 degrees. Nothing in my mind particularly difficult about that. It's literally just identifying the correct trig identity and applying it. Yes, sir. No. The one that is going to pop up the most is converting sine to cosine. And the others would be if you have a negative magnitude, which we're going to tackle in the next thing. That would be another one to use. So if you have a negative magnitude, just shift the angle by 180 degrees. We're never going to be in a point where we really need to convert cosines to sines, because when we get into our frequency domain for circuit analysis starting next Monday, but we'll do a little bit of it today, we're going to establish the cosine function as our baseline. So everything will be in reference to that. So if we can convert from sine to cosine, we're good. If we know how to convert a negative magnitude into a positive magnitude, which is just shifting by 180 degrees, we're good. All those trig identities where it's, sine of alpha plus beta is equal to blah, blah, blah. Complex numbers take care of all of those relationships. So you do not need to remember those. Okay. All right. So for part B here, we have g of t is equal to negative 4 sine 3 pi t plus 30 degrees. So if we apply the exact same trig identity that we just used, where sine of x is equal to cosine x minus 90 degrees, this becomes negative 4 cosine 3 pi t plus 30 degrees minus 90 degrees, which we can obviously write that as minus 60 degrees. And lastly, we're going to apply the identity that negative cosine of x is the same as cosine of x plus or minus 180 degrees. And so this gives us positive 4 cosine 3 pi t. So we have plus 30 minus 90 is negative 60, plus 180 degrees would give us positive 120, minus 180 degrees would give us negative 240. Both of those answers are correct. I just went with the one with the positive sign. The reason why both of them are correct is plus 120 degrees is about right here. Negative 240 degrees is just the same angle measured going the opposite way around our circle. So that's why you can add or subtract 180 degrees. Part C is the one that can be very, very difficult or very, very easy depending on the way that you approach it. I'm going to set up the difficult way just to show you that it's going to be a nightmare real quick, and then we'll talk about the easy way to do it. So h of t is 14 sine 50t minus 5 degrees minus 10 cosine 50t. Well, we could rewrite that 14 sine 50t using one of those ugly trig identities I told you that we didn't need to remember, right? So for example, if this guy is alpha and this guy is beta, we have sine alpha minus beta is, I believe, sine alpha cosine beta minus cosine alpha sine beta. Let me double check that just real quick. A minus, there we go. Yeah, so sine A minus B is sine A cosine B minus cosine A sine B. I'll be damned, I remember it. So if we put that 14 out front here, this would be 14 sine 50t. Why is my pen not writing where I want it to write? Cosine 5 degrees minus 14 cosine 50t sine 5 degrees. Well, cosine of 5 degrees is just a number, and sine of 5 degrees is just a number as well. Oh, and I'd still have minus 10 cosine 50t out here. So if I get out my calculator, I could see 14 cosine 5 degrees is 13.947 sine 50t. 14 sine 5 degrees is 1.220 cosine 50t minus another 10 cosine 50t would give me 13.947 sine 50t minus 11.220 cosine 50t. And now I would effectively have to use an inverse relationship to go back the other direction, right? And so what I mean by that is if I want it in the form cosine of alpha plus beta, I would have to use the trig identity. I believe it's cos alpha cos beta minus sine alpha sine beta. Let me double check that. Yep, cos alpha cos beta minus sine. Yeah. So I would have to then apply this guy and work my way backwards to get into that form. Okay. Tedious. It's not super crazy, ludicrously hard by any stretch of the imagination, but it takes a bit, right? We're 4 steps in and we're less than halfway done. So this is the hard way, and it is bad, okay? Now let's talk about the easier way. H of t is 14 sine 50t minus 5 degrees minus 10 cosine 50t, right? If we use that first trig identity, this means that we have 14 cosine 50t minus 95 degrees minus 10 cosine 50t. We okay thus far. This is equal to the real part of the complex number 14e to the j 50t minus 95 degrees minus the real part of 10 e to the j 50t. These complex numbers are quantified by the same 3 things as their cosine counterpart, right? They have a particular magnitude. So this is the magnitude of the complex number. It is the exact same thing as the magnitude of the sinusoidal function. This is the frequency of the complex number. It's the exact same thing as the frequency of the sinusoidal function. And lastly, we can see that they are also quantified by their phase angle. So we have negative 95 for the phase angle of the first bit, and that's the exact same thing as the phase angle of the sinusoid. So h of t is going to be the real part of 14 angle negative 95 degrees minus 10 angle 0 degrees. we can literally just subtract those two complex numbers, and we're going to wind up getting the exact same result as if we had done all that terrifying amount of trig. So this would be the real part of 14 angle minus 95 minus 10 17.899 or 900. Let me see what I used up here. 900. Making sure I'm rounding the same way. Angle negative 128.817 degrees, which is simply 17.900 cosine 50t minus 128.817 degrees. And that is exactly what I get here. So on your homeworks, exams, all that kind of good stuff like that, save yourself the immense headache of learning to apply all those trig identities and just convert your sine functions to cosines and then treat everything like a complex number, and the math becomes trivial. If you go the other route, again, it's trig identity after trig identity after trig identity, forwards and backwards to get something that your calculator can do in 2 steps. So that's part C. The easy way. So for example, just let's pop over to the web work real quick and look at what's going on. So this is leading and lagging. We'll talk about that in just a moment. But for this problem right here, it says we're trying to find A, B, C, and the angle theta if 15 cosine 100t minus 179 degrees minus 51 sine 100t plus 178 degrees is equal to A cosine our frequency plus B cosine our frequency. So that's splitting it up like we just did in the previous problem, or expressing it as a single sinusoid. So just for the sake of argument, let's check whether the method I just said works for C and our phase angle here. So I am suggesting that we are going to be adding the complex numbers 15 angle negative 179 degrees, and then we're going to have minus 51 angle 178 minus 90 is 88, right? So the result I get is 73.266.045, putting in lots of significant figures so it likes me. Negative 134.96168. Oh, let's see what I did wrong here, because I'm very surprised that that did not work. Let's see. 51, 178, hold on. 88, yeah. I feel like a jackass. $15 so that's C and phi, right? All right, 15 angle negative 179, right? So that's the magnitude of this guy is 15. The phase angle is negative 179 degrees minus 51 angle 178 minus 90. Okay, there we go. 53.908 with an angle of negative 108.1331. So I must have typed something in wrong the first time I put it in. But anyway, the method works when you're not a jackass who puts numbers in their calculator in incorrectly, apparently, which happens to the best of us because I'm the best of you. Sorry. How would we go about, just for the sake of argument, how would we go about figuring out what parts A and B are for this problem? Anybody got any ideas here? What did we do literally at the beginning of the first problem, right? So the point of A and B, if we look at this problem statement, we're putting it as the sum of a cosine function plus a sine function, okay? If we look at what we did, what do we have right here? A cosine function with no phase angle and a sine function with no phase angle, right? So it's literally just applying these simple trig identities here to get rid of that phase angle. That's it, okay? So nothing, literally stopping at the point I stopped at was on purpose to show you how to do those types of problems. Okay, so now let's look at problem 2 down here. So it tells us, or it asks us to determine the angle by which a current I of t leads a voltage V of t if V of t is equal to 10 cosine 10t minus 45 degrees. So what I'm going to do is use the phase diagram method because I find it to be much, much easier than looking at the sinusoidal functions themselves. So I'm starting out with a polar plot, which means horizontal axis over here is 0 degrees. This is 90 degrees. This is plus or minus 180 degrees. And this is negative 90 degrees. And I'm going to draw my voltage V of t, okay? So it's 10 angle negative 45 degrees. The magnitude here actually doesn't remotely matter. Negative 45 degrees is going to be right around here. So this is how I would represent V of t on my phase diagram. Simply by a vector pointing at a negative 45 degree angle from our horizontal axis, okay? IA of t is given as 5 cosine 10t. So we have our magnitude of 5, and we're just going to go out along the horizontal axis because our phase angle is 0. So the question asks us to determine the angle by which I of t leads V of t. So what we're going to do, and I'll do this in pink, I guess. V of t is our reference angle here, right? If we're finding how much I of t leads or lags it, we need to start measuring at V of t. If we want to measure leading, we go counterclockwise and lagging is clockwise. The reason why leading is clockwise, so if we think about what a phase angle means, right? If a phase angle is positive, so let's say that I have, let me draw just a very simple thing here. So this is time, and I'm going to attempt to crappily draw a sinusoidal function. Like so, all right? So this guy is just a plain old cosine omega t, right? I know it's a cosine function because at t is equal to 0, it's at its peak value. If I drew another cosine function with the exact same frequency, this is a cosine function, but it's shifted slightly to the left. which means its peak value is occurring earlier in time than our function cosine of omega t. So this green guy would be cosine omega t plus some phase angle theta, where theta is positive. So this means it's occurring earlier in time. That's exactly why we measure leading as counterclockwise away from our angle, because when we go counterclockwise, we're getting a more positive phase angle, which indicates that it's leading. Its peak value occurs earlier in time. We measure lagging as counterclockwise because it has a more negative phase angle, which means it's delayed more in time from our reference, okay? So it might seem counterintuitive, but that's the way it's gotta go. You raising your hand? So we're measuring the angle by which I of t leads V of t. So that's specifically saying that V of t is our reference. So if we wanted to know the angle by which V of t leads I of t, for instance, we would start measuring from I of t and go counterclockwise around. And we would see that our angle would be, let's see, 90 plus 90 plus 90 is 270 plus 45 is 315. Yeah. So it's all in the problem statement as to which one we choose to be our reference for this particular problem. Yeah. No, so we chose V of t because the problem told us to. There is no particular convention or anything like that. Now, that being said, when we get into our steady state sinusoidal circuit analysis, particularly when we're talking about the concept of a power factor. Power factor is always measured by how the current is behaving with respect to the voltage. So if the current is lagging the voltage, we say that we have a lagging power factor. And if the current is leading the voltage, we say that we have a leading power factor. That's literally the last topic we'll talk about in this class. So we're a little bit ahead of the game there. Yeah, to this point, it's literally just measure it the way the problem tells you to, and you're good to go. So with that out of the way, what then is the answer for part A? If we start measuring from our voltage and we're measuring counterclockwise, what is the difference between those two signals in angle? 45 degrees, yeah. So we're always measuring from here and counting positive, okay? So even though V of t has an angle of negative 45 degrees, we have to increase by 45 degrees to reach our horizontal axis. So we would say that I of t leads V of t by 45 degrees. And then we could do parts B and part C in a very similar fashion. So let's take a look then at the web work problem dealing with leading and lagging. Because this is a problem where the shortcomings of web work become extraordinarily obvious. So let's look at this first problem here. It tells us to find the angle by which I1 lags V1. So again, we have our voltage signal as our reference. If the voltage V1 is 230 cosine or frequency minus 69 degrees. So I'm going to draw that. I'm going to try to draw that. So here is our phase diagram. And our voltage angle was negative 69 degrees. So that's going to be somewhere around down here. And if we look at our problem statement, it tells us that I1 is 9.5 cosine 120 pi t plus 17 degrees. So with an angle of positive 17 degrees, our current is going to be right around here. We are trying to find, just to be clear here, the angle by which I1 lags V1. So lagging means we should be measuring counterclockwise, right? So this angle between this 69 here is going to be, let's see, 21 degrees plus another 90 plus 90 plus 73, right? So 21 plus 90 plus 90 plus 73 gives me an angle of 274. Now I'm going to type that into WebWork, and I'm willing to bet it's going to tell me I'm wrong. Yep, it tells me I'm wrong. The reason it tells me I'm wrong is because WebWork can't differentiate between 274 degrees and negative 86 degrees. It doesn't understand that if you add or subtract 360 degrees from an angle, it represents the exact same angle. So I'm going to try negative 86. And voila, I've got the right answer. The method that I am describing to you is perfectly correct. It's just a fundamental flaw in WebWork's interpretation here. So if you're sure you're doing this problem right, try adding and subtracting 360 degrees from the answer you get, and I'm sure one of those is going to be what WebWork accepts. So it's just something that's come up literally every quarter. I don't know why it was programmed this way, but it was. So any other questions about leading and lagging? Do we want to work any more of these, or is it, I feel it's a fairly straightforward concept. The only real thing I want to point out here, if we look at part B, our signal is expressed as a sine function. We're going to be using cosine as a reference. So you're going to need to convert that guy into a cosine function. Same thing for part C. It's a cosine function, but it has a negative magnitude. So you're going to need to convert that to have a positive magnitude before you can do the comparison between the angles, which I believe are literally the things that I tell you in the first video of how you compare angles. Make sure they're both cosine functions and make sure they both have positive magnitudes, and you're good to go. All right, so let's go back to the in-class assignment here and look at problem 3. And this is where stuff's going to be a little bit new, but that's okay. So problem 3 says, express the following time domain signals as phasors in the frequency domain. This is one of the most fundamentally important concepts in this class, and you would be absolutely amazed at how easy it is to employ, okay? Just turn around. Yeah. So here's phasors in a nutshell, and there's a 10-minute video telling you the same thing. In the time domain, we have a generic voltage signal. Let's call it V of t is equal to Vm cosine omega t plus some phase angle theta v, right? Sinusoidally varying cosine function with a particular phase angle. And what I'm going to call the mixed domain, V of t is simply the real part of our complex number Vm e to the j omega t plus theta v. This is exactly what was shown in the video. In the frequency or phasor domain, we would represent this time domain signal as phasor voltage V. So that's that bar over it means it's a complex number, is simply Vm angle theta v. So it's the exact same thing that we had in the mixed domain, except we've suppressed the time varying frequency term. That's it. So if we look at part A here,
VA of t, how can we express that as a cosine function with a positive magnitude? How would we do it? Plus or minus 180 on the phase angle, right? So we're going to change negative 10 to positive 10 cosine 4t, and let's subtract 180 degrees for argument's sake here so that our final angle lies somewhere between positive 180 and negative 180. It's going to have the smallest possible value. So 75 minus 180 is negative 105. From this, our phasor voltage V is 10 angle negative 105. That's it. That is how you convert to a phasor. I know you guys probably think I'm pulling your legs when I say this is one of the most fundamentally important concepts in this class. It really is, and it really is that simple. Literally, whatever magnitude you have and whatever phase angle you have, that's the information you keep, and that's how you define a phasor. It's that simple. So let's look at part B here. And you guys are going to tell me what to do. Yeah, so I've got to convert my sine to a cosine function. So how am I going to do that? Subtract 90 degrees. Okay, so that's going to give me 5 cosine 20t minus 100, right? So what is my phasor voltage VB of t, or VB? 5 angle minus 100. Easy peasy. Lastly, well, so part C here, this is just going back to what we did on problem 1. We have two sinusoidal functions and we have to add them together. So we could suffer through all the terrible trig, or again, just treat them as complex numbers from the start, add them together, and it's easy enough. So let's go past that. The last problem here has to do with impedance. And I'm gonna hold that one. We'll readdress this guy come Monday, because I'd like to spend the rest of the time talking about some phasor relationships real quick. So this is what I'm looking for. Nah. I don't check when you actually turn them in. So, I mean, you can wait or not. If it's turned in, you get credit. That's my motto. This is a participation grade. So whenever you choose to participate is good by me. It can be on the last day of the quarter trying to pull your grade up, or you can be caught up on things. Either way is fine by me. So yeah. All right, so our phasor voltage. So again, we have, let's not do pink. V phasor voltage is going to be Vm angle theta V, which is just a shorthand notation for Vm e to the j theta V. All right, so I'm saying I can write that exponential form as is identical to our phasor representation where we don't have a frequency term, okay? And I could just as easily say then that a phasor current I would look something like Im angle theta I is equal to Im e to the j theta I. So we can use this to actually analyze a circuit. So let's take our generic RL circuit that we suffered with here's R and here's L, okay? So I'm gonna put a line right here and we're gonna do something. We're trying to find this current I of T, okay? So if we look at this guy in the, let's say that we have a resistor, okay? Here's our resistor R. We have some voltage, V of T, and some current I of T, like so. What is the fundamental relationship that relates our current to our voltage for this resistor? Ohm's law, right? Nothing, not a trick question whatsoever. We know that V of T is equal to R times I of T. Well, if we use our phasor relationship then, so if we have a sinusoidally varying system, then that simply means that V is equal to I times R. V phasor is equal to I times R. Nothing wild or crazy there, okay? Let's say instead we have an inductor. It has a value of L. Here's our voltage drop VL of T. Here's our current IL of T. So our relationship here is VL of T is equal to L di by dt. Okay. If VL of T is Vm e to the j omega t plus theta v, then on the other side, we're going to have L times d by dt of Im e to the j omega t plus theta I. So we're working in the mixed domain right now, okay, just to be clear here. Both, so this would be Vm e to the j omega t e to the j theta v is equal to j omega L Im e to the j omega t e to the j theta I. So I've simply expressed that exponential where I have the sum of two angles as two individual exponential functions that are multiplied by each other, right? I have a common factor there and a common factor there, which leaves me with Vm e to the j theta v is equal to j omega L Im e to the j theta I, or phasor voltage V is equal to j omega L times phasor current I. This is the current voltage relationship in phasor form for an inductor. Well, we can use this, right? So, analyzing our original equation, we have our phasor voltage source is going to be equal to the voltage drop over our resistor R, which is just phasor current times R, plus the voltage drop over our inductor, which is just j omega L times our phasor current I, right? So from this, our phasor current I is just our voltage divided by R plus J omega L. And we could put in numbers and we have solved our circuit in literally just a couple of steps. That's how these complex numbers are going to make our life so much easier, right? Our solution has gone from 3 pages of trig to roughly a page and a half of complex numbers to a very, very simple algebraic statement. And we are going to introduce the concept of impedances in the next video or whatever, and that's effectively going to formalize all of these relationships for our different components. And we'll find that earlier in our transient analysis circuits and all that kind of stuff, we saw that inductors in series added like resistors in series, inductors in parallel added like resistors in parallel, capacitors in series added like resistors in parallel, and capacitors in parallel added like resistors in series. Not particularly complicated relationships or anything like that, but could be a little bit tricky because you got to think about things. When we're in the frequency domain, we will find out that we can effectively treat all resistors, capacitors, and inductors as a single quantity called an impedance, which behaves just like a resistor. Impedance is nothing more than effectively a frequency-dependent resistance that we're going to be dealing with. So it scales with omega. And it will allow us, again, to treat all of our circuit elements, our components, resistors, capacitors, inductors, et cetera, treat them like resistors, just some of them are imaginary. But, so we'll have complex numbers. But other than that, everything is going to go to DC circuit analysis because we're using these simple phasor relationships. So this is all to get rid of doing terrifying amounts of trig in calculus. All right, that's enough out of me for today. So I'll see you guys on Monday. Well, we'll start actually knocking out some real frequency domain circuit analysis stuff. All right, so it's 1:30, so let's get started. And by that, I'm not sure what to do today. How many of you actually watched the hour and 7 minutes of brutal mathematics that I forced upon you? Yeah, that was a bit of punishment. Not intentionally, but there was a lot of terrible math going on in there. And what we're going to be learning about from Monday and on is how to avoid that terrifying amount of math. We can do some of that today, and I'm happy to do it, but I kind of just want to feel out like if you guys had any questions on anything about that, or if you want to look at the in-class assignment or the homework assignment associated with it, how do you want to approach all that nasty, ugly trig? Anybody have any thoughts other than scrub it from your brain forever? Okay, so let's look at the in-class assignment then, and then apply what we're learning there to some of the web work problems specifically. Okay, that's what I did in the earlier one, and it seemed to work okay. So to that end, let's look at our in-class assignment here. So problem 1, very hopefully simple and straightforward for the most part, at least until we get to part C. Problem 1, part A, it's asking us to express each of the following sinusoidal functions as a single cosine function. So if we look at part A, where we have f of t is equal to 300 sine 628t, there is a trig identity that tells us sine x is equal to cosine of x minus 90 degrees. So if we simply apply that trig identity directly, we can easily see that this becomes 300 cosine 628t minus 90 degrees. Nothing particularly difficult about that one. For part B, the level of complexity is increased a little bit because we have a negative magnitude. So we have negative 4 sine 3 pi t plus 30 degrees. So we can convert that to a cosine function by saying we have 4 sine 3 pi t, and positive 30 degrees minus 90 degrees gives us negative 60 degrees. Nothing wild or crazy there. But now, sorry, there should be a negative sign right here. But now we need to figure out how to get rid of that negative sign. And that's another simple trig identity that says that negative cosine of x is equal to positive cosine of x plus or minus 180 degrees. Literally does not matter if we add or subtract the 180 degrees here. I am going to add 180 purely because I want my angle to have the smallest possible magnitude, right? So if we subtracted 180, it would be negative 240 degrees, which is the smallest way to represent that angle. So I'm just avoiding that. So we would have oh goodness here. This should not be sine, this should be cosine because we subtracted the 90 degrees. And then here we have 4 cosine 3 pi t minus 60 plus 180 is plus 120 degrees. Pretty easy peasy. Now, part C here is where things, there's two approaches. One is very difficult and the other is very easy. And I'm going to outline at least the beginning steps of the difficult process because it's actually going to help us with the homework. And then we're going to pump the brakes. I'll explain how you could go further, but it's going to be very, very similar to that long trig explanation in the video lecture. So this function h of t is equal to 14 sine 50t minus 5 degrees minus 10 cosine 50t. So I'm going to apply the trig identity that says sine of alpha plus beta is equal to sine alpha cosine beta plus cosine alpha sine beta, where 50t is alpha and actually let's do sine alpha minus beta, which if I'm not mistaken just changes that sign. Let me double check that real quick. Refresh. Yep, alpha minus beta has the alpha sign or the negative sign in the middle. Okay, so if we apply that trig identity, this is going to become 14 cosine 5 degrees times sine 50t minus 14 sine 5 degrees cosine 50t minus 10 cosine 50t. I've rearranged things slightly here, so I have 14 cosine beta sine alpha minus 14 sine beta cosine alpha. The reason I'm doing that is because cosine of 5 degrees and sine of 5 degrees, it's just a number, right? It's a number line somewhere between -1 and +1. So 14 times the cosine of 5 degrees is 13.947. Multiply that by our sine 50t. 14 sine 5 degrees is 1.220. Minus our 10 cosine 50t. And now we can group together the two cosine functions, right? So that would be 13.9, sorry, that's not 13. 13.947 sine 50t minus 11.220 cosine 50t. So those 4 steps that we have done there have served to effectively get rid of our phase angles, right? So where we would go from here would be having to use the identity cosine alpha plus beta is equal to cosine alpha cosine beta minus sine alpha sine beta. We would effectively have to use this trig identity almost backwards to be able to come to convert this into a single cosine function. So what I mean by that is, let's put A here, and then this would be an A. So if alpha is 50t, then we would have, let's see here, if alpha is 50t, excuse me, yeah, alpha is 50t. So we would have negative 11.220 is equal to A multiplied by cosine beta, and we would have 13.947 would be equal to negative A sine beta. And we would have to use further trig identities in order to figure out what A and beta are, where A is the magnitude of our single cosine function and beta is the phase angle of our single cosine function. So there's probably, I think, at least 4 more steps left in there to get to our final answer, okay? So not insurmountable, but it would be somewhere between 8 and 10 steps to convert our original function into a single cosine expressed with a phase angle, which is an awful lot of work to do when you have to know all those different trig identities and all that kind of jazz. So this is the beginning of the hard way to do this. So just so we don't spend another 10 to 15 minutes on this one problem, let's talk about the easy way. Again, we start with h of t is equal to 14 sine 50t minus 5 degrees minus 10 cosine of 50t. And now what we're going to do is we're going to convert that sine function into a cosine function, okay? So that would give me 14 cosine 50t minus 95 degrees minus 10 cosine 50t, right? Easy enough there. Using the complex relationship that was discussed in the second video, h of t is then simply going to be the real part of 14 e to the j 50t minus 95 degrees minus 10 e to the j 50t. You may be saying to yourself, well, gosh, how does that make this any easier? Well, using our polar form shorthand notation, this is simply 14 angle minus 95 degrees minus 10 angle 0 degrees, which we can do in our calculator. So take a moment to do it. give me the answer in polar form, not rectangular form. That's still rectangular form. Give me the answer in polar form. Hit options and then down and then 1. $128 point what, please? All right. So the real part of that complex number, using Euler's identity, is 17.9 cosine our frequency of 50t minus 128.8 degrees, which is exactly the answer that we have here. Now, I made these assignment sheets and I'm doing this work, so you may effectively call bullshit on this methodology. So what we're going to do is we're going to see if it works in the web work, which I didn't make. All right, simple enough. So if we look at this problem 2 on homework assignment 19, it asks us to find A, B, C, and our phase angle, where if we look over here to the right, the form that I'm asking you to get your answers in for that first problem is exactly the same as this bit here, right? I want some magnitude cosine omega t plus our phase angle. So in this case, we have our first part of our function is 15 cosine 100t minus 179 degrees. So we would represent that as 15 angle negative 179. Our second bit is 51 sine 100t plus 178. So we need to convert that to a cosine function first. So that's 51 angle 178 minus 90 degrees. I'm literally just putting 178 minus 90 in the calculator so I can be lazy. And when I do that math, I get an answer of, I can find my cursor, there we go, 53.908014, just putting in lots of significant figures for web work. And my angle is negative 108.1331 degrees. And I'm going to check my answers. I'm correct. So if we wanted to brute force the trig up here, we could absolutely do it and show that we're going to get the same answers. But to me, it's a waste of time, right? So I would highly suggest that whenever you're asked to find the sum or the simple addition or subtraction, etc., of sinusoidal functions, instead of bogging yourself down with tons and tons of trig, convert everything to a cosine function and then treat it as complex numbers, and you'll get the answer in a trivial amount of time. Your calculator can do that. It can't add these sinusoids together. If we look back at that problem, we didn't figure out what A and B are here. But if you'll notice, A and B is literally, how to find A and B is literally what I did to set up the hard way before I used my trig identities to go backwards to convert it into a single cosine function, okay? So this problem should be fairly straightforward for you guys to figure out. I would argue that at the most I would ask of you on your next exam would be how to put it in the C cosine omega t plus phase angle form. I wouldn't make you split it up into a sum of a sine function with no phase angle and a cosine function with no phase angle or anything like that. It's just too tedious. And we'll find out when we start doing our frequency domain circuit analysis that effectively all of the signals that we're going to look at are going to be of this form: magnitude, cosine, omega t plus phase angle. So that's why we're going to be focusing so heavily on that part. So any questions about this particular homework problem or how to approach that first in-class assignment problem then? Hopefully. Sure. Okay. So how I would get as, let's see, so A is the coefficient for the cosine function, right? Cosine without a phase angle. So let's see, I have 15 cosine 100t minus 179. So I'm going to have to do this over here. I make that window small. Back where it was. All right, so I had 15 cosine 100t minus 179 degrees, right? Minus 51 sine 100t plus 178 degrees. Is that correct? Let's check just to make sure. Minus 179 plus 178 minus sine in the middle. Okay. So I'm going to be using the following two trig identities. Cosine alpha minus beta is equal to cosine alpha cosine beta minus sine alpha sine beta. And I'm going to use sine alpha plus beta is equal to sine alpha cosine beta plus cosine alpha sine beta. So that means for this first term here, I'm going to have 15 cosine 179 degrees times cosine 100t minus 15 sine 179 degrees sine 100t. So that's me converting this first term minus, this is all one line of math, okay? 51, let's see, so sine 15 cosine positive 178 degrees sine 100t plus 51, let's see, so cosine of alpha sine 178 degrees cosine 100t. Close this off. I got to get my calculator out. So 15 cosine 179 is negative 14.998 cosine 100t. 15 sine 179 is negative 0.262 sine 100t. 51 cosine 178 is negative 50, so minus negative is plus 50.967 sine 100t, and then finally 51 sine 178 is positive 1.780 cosine 100t, and that negative sign means I have a negative sign here. Now I combine my like terms, so I have negative 14.998 plus delete minus the 50.967, which gives me 35.971 cosine 100t, and I'm going to have negative 0.262 minus the 1.78 gives me negative 2.042 sine 100t. So again, lots of trig. And we will get, let's see, let's throw this into WebWork, 35.971. I'm going to show you guys another trick in just a second. 35.971. For B, I get negative 2.042. And let's check my answers. What did I screw up? Let me see if I'm just not doing enough things. No, I've made some dumb mistake somewhere. All right, let's check my trig identities. All right. So this is alpha, this is alpha 1 and beta 1, this is alpha 2, beta 2. So 15 cosine beta cosine alpha, that bit's correct. Oh, plus, you're absolutely right. That should be a plus sign right there. Thank you. So that means, oops, a plus sign here. Dang it. You're right on that trig identity. So that would be plus right here. Right. 51, so let's see. Cosine beta sine alpha. 51 sine beta cosine alpha. Okay. So let's just double check this real quick. 15 cosine 179 is negative 14.998. So that bit looks correct. 15 sine 179, positive 0.262. So that bit's correct. Then I have 51 cosine 178. That's negative 50 multiplied by that negative sign gives me positive. 51 sine 178, 1.78 multiplied by that negative number there. Negative 14.998 plus 50.967, 35.969, 0.262 minus 1.780, negative 1.518. Let's see. Oh, no, that's not. That's a 15, that's a 51. Because the answers that I'm getting are still nowhere close to these. And I don't know why that is. Let me look at it one last time here. I'm in degree mode, so that's good. All right, so just double checking this trig identity a third time here. Cosine alpha minus beta is equal to cosine alpha cosine beta plus sine alpha sine beta. Let me double check that part. Cosine alpha cosine beta plus sine alpha sine beta. Okay, so that trig identity is right. Sine alpha plus beta is sine alpha cosine beta plus cosine alpha sine beta. All right, so the trig identities are correct. So if alpha is 100t, so I have 15 times the cosine of alpha times the cosine of beta plus 15 times sine alpha 1 sine beta 1. That bit's correct. Oh, I'm making the dumbest possible mistake. 1.780 here. The dumb mistake I'm making, I took the cosine term here, but I didn't add it to the cosine term over here. I added it to the sine term. So I just wasn't paying attention. So it should be negative 14.998. Minus 1.780 is negative 16.778 cosine 100t. And then I have positive 0.262 plus 50.967, 51.22, oops, 229 sine 100t. All right, so negative 16.778 and 51.229. I bet this person in chat. Oh, okay. Thank you, Garrett. I just thinking out loud here, just trying to make sure I'm being less of a jackass than normal. All right, so let's circle back around to that. So negative 16.778, that seems about this. And 51.23 seems like pretty dang close to the 51.229 that we got. All right, so that was the longest possible way to do that part. Now let's talk about the shortcut. So we have our C cosine 100t plus phi bit, right? Like we got that for sure correct. So I'm going to put in the complex number 53.908014 with an angle of negative 108.1331. And I'm going to express that complex number as a rectangular form complex number. What I get is negative 16.778 minus 51.230. So I get the exact right part for A, the coefficient for the cosine term, but I get the negative of the coefficient for the sine term. And that's because if we look at our trig identity, when we have a minus sign here, we have a plus sign there and vice versa. That's literally it. So we can take the rectangular form of our complex addition and get the coefficients for the sine cosine function plus sine function representation as well. So the complex numbers literally make all of this math wildly easier than all these silly trig identities, and then my inability to recognize that I'm adding the wrong things. All right, so any further questions on this problem or that associated homework problem? All right, I hope we beat that to death because we spent roughly 30 minutes on it. So let's take a peek at in-class assignment problem number 2. So this one is all about leading and lagging signals. So I'd like to address that. So we're going to approach this problem using a phase diagram method. So I'm simply drawing a plane here, and I have 0 degrees, 90 degrees, plus or minus 180 degrees, and then negative 90 degrees in here. And so I'm just going to represent my sinusoidal signals at a snapshot in time on this polar plot, okay? So I'm effectively saying at time t is equal to 0, what is this guy going to look like? So my voltage signal, which I'll do in red, is going to be 10 with an angle of negative 45 degrees measured from our horizontal axis. So my voltage signal is going to look something like this, where this angle is supposed to be negative 45 degrees. For my current, let's do IA. That's easy enough. I can explain everything through that one. My current IA would be 5 with an angle of 0 degrees. So something like this. So here's IA of t. The problem statement tells us to determine the angle by which I of t leads V of t. So what that means is that we're going to consider V of t our reference, and we're going to make all of our measurements from V of t. So if I go in this direction, so if I go counterclockwise, this is leading, and I'll explain why momentarily. And if I go clockwise, this is for lagging. So it says I want the angle by which I of t leads V of t. So what I'm going to do is I'm going to start from V of t and then just measure the angle counterclockwise until I hit IA of t. So what would that be? So I start here and go counterclockwise. How many degrees until I hit the positive horizontal axis? 45, right. So from that, IA leads V of t by 45 degrees. It's literally that simple, okay? Now, I want to take another moment to explain why counterclockwise is leading and clockwise is lagging, because it may seem counterintuitive. So if I have a simple cosine function, so this is supposed to be representative of simply something like cosine omega t. No phase angle, and we can tell there shouldn't be a phase angle because the positive peak occurs at t is equal to 0, okay? I'm going to now draw another cosine function. And this guy right here was simply cosine omega t plus some phase angle theta, where theta is positive. So if we time shift to the left, our phase angle should be positive. If we time shifted to the right, our phase angle should be negative. Our function in green leads our function in red because its positive peak occurs literally earlier in time, right? So the positive peak happens at an earlier point in time than the positive peak for our red curve. So that's why it's leading. If we look at our graph here, Measuring counterclockwise is leading makes sense because when we measure in that direction, we're getting more positive angles, right? If we had something that was lagging, meaning that it was time shifted to the right, it would have a negative phase angle associated with it. And so that's why lagging is measured counterclockwise, because if it has a more negative phase angle, it's lagging behind the reference signal. Does that make sense? So leading is counterclockwise because we're getting a more positive angle. Lagging is clockwise because we're getting a more negative angle. Now let's take this relationship and apply it to a homework problem. Or two, because we're kind of running out of time here. Let's see. Web work. Problem 1 is the one with leading and lagging. All right, so let's do 1B. So it tells us to find the angle by which our current I1 lags our voltage V1 if V1 is 230, which the magnitude doesn't particularly matter, cosine 120 pi t minus 69 degrees. So I'm going to draw V of t real quick. So that's angle negative 69. 0, 90, plus or minus 180, minus 90. All right. So negative 69 degrees is going to be somewhere around here. This is V1. We're looking at our part B here. We have 8.2 sine 120 pi t minus 112 degrees. So what we have to do is we need to convert that sine function into a cosine function. Anytime we are going to compare signals, they need to both be expressed as cosine functions, and they both need to have positive magnitudes. So how do I convert 8.2 sine blah, blah, blah to 8.2 cosine something? How did we do it 20 minutes ago? Subtract 90 degrees. Yeah, that's it. So that would be negative 112 minus 90 is negative 202, which is the same as positive 158. I've just shifted it by 360 degrees. Okay. So let's see, 90, somewhere around this area. If we went around like this, it'd be negative 202 degrees. And if we went this way, it would be positive 158 degrees. I'm drawing both to see which way it makes our math easier here. All right, so let's see what the question asks us again. We want to find the angle by which I1 lags V1. So that means we're going to be looking, starting from V1, and we want lagging, so we go in this direction, clockwise. So how many degrees do I have to go measuring from this guy to hit this point over here? Well, this guy right here looks like 21 degrees, right? To where I hit the negative 90. Then I have another 90 degrees to go all the way through this quadrant. And then let's see, I have 22 degrees over here. So if I add 21 plus 90 plus 22, I get 133 degrees. So I'm going to pop over to WebWork, type in 133 degrees. And there is a very distinct possibility that WebWork is going to tell me this answer is wrong, and I will explain why. Oh, well, it told me it was right. Dang it. So the reason why I'm frustrated with that is because WebWork has a bit of an issue in as much as it cannot distinguish between, say, the angle of 0 degrees and 360 degrees and negative 360 degrees. It does not recognize that all three of those represent the exact same thing. So for instance, on the first problem here, when I worked it with the earlier class today, if you do the method that I prescribed, you would get positive 274 degrees, which WebWork says is wrong. If you subtract 360 from that, you get this exact answer, which it interprets as correctly. So when you're doing these leading lagging problems, if you're sure you're doing it correctly and WebWork tells you that the answer you're getting is wrong, simply add 360 degrees and check it. If it still says it's wrong, subtract 360 degrees from your original answer. One of those is going to be correct. Okay, it's literally just WebWork doesn't understand that these are angles and multiple angles can represent the exact same thing. That's all it is.
After you did a negative 112, expected 90%, that you added, you had that?
That is correct.
And then you did
well, so let's look at let's look at exactly what I did here. Okay, so I treated it. I subtracted 90, which gave me negative 202. Okay, so what I did is I literally measured from this phasor V1 here. So it's positive 21 degrees to get over to this negative vertical axis, right? Then 90 more degrees to get to the negative horizontal axis. Then 22 more degrees to get to this point, which is representative of my negative 202. Because 180, or negative 180 minus 22 is negative 202, correct? Minus 22, yeah. So all I did was I added up the amount, the angle I needed to get to the negative vertical axis, the angle I needed to get to the negative horizontal axis, and then the angle I needed to get from there to the actual angle that I'm measuring. I could have, let's see, how else could I? No, I mean, that's literally just the way to do it. The only other way I guess I could have done it, if I would went in this opposite direction and counted everything as a negative angle, that would also work. So the key here, all right, so let's work at another problem with this just to hopefully illustrate it, all right? And Karen, I'm gonna put you in the driver's seat, literally meaning you get to tell me what signals we're looking at, whether we're looking leading, lagging, etc. Okay? So give me a voltage signal. Give me a phase angle. Positive 39 degrees, all right? Now give me a current signal. What's the phase angle? Those are too close. Give me some, well, that'll work. Negative 130, okay. All right, now am I trying to find how much the voltage leads the current, how much the voltage lags the current, how much the current leads the voltage, or how much the current lags the voltage? All right. So how I would approach this problem, again, labeling my axis 0, 90, plus or minus 180, negative 90 here. I'm going to draw my voltage signal first. 39 degrees is going to be something like this. Now I'm going to draw my current signal. Negative 130 degrees is going to be somewhere around here. If I want how much my current lags my voltage, then I start measuring from my voltage, and because I want lagging, I'm going to go clockwise, okay? So I have this 39 degrees, plus this 90 degrees, plus this 40 degrees, gives me I lags V by 169 degrees. That's the process, right? So if I wanted instead, let's say how much the voltage lags the current. I'll do this guy in purple. I would start measuring from my current, and because I want lags, I would go this way, right? So that would be, let's see, so if this is a 40 degree, then that means this is 50, 90, and let's see, 90 minus 39 is 51, so that would be V lags I by 191 degrees. And the answer to these two things better add to 360 because I've gone the full way around the circle. Okay, so it's literally just draw your things on a phase diagram. So you don't care that it's a cosine function, or everything needs to be expressed as a cosine function, but you're not drawing a cosine, right? You're taking a picture of this thing at exactly t is equal to 0, and then just plotting the angle on this graph. You're doing that for both of your signals. Figure out which one is your reference, and then if you want lagging, measure counterclockwise, or excuse me, lagging, measure clockwise, leading, measure counterclockwise. So all those guys should be pretty trivial. All right, let's take a moment. We literally have 1 minute left, so I want to look at WebWork problem 3 here because I get a whole heck of a lot of questions about it. I got no problem answering them, but this problem isn't nearly as difficult as you guys seem to think it is. So for problem 3, you're told that you have a sine wave f of t is 0 and increasing at t is equal to 5.1 milliseconds, and the succeeding positive maximum of 11.5 occurs at time t is equal to 9.1 milliseconds. And then you're asked to express that function as a sine, as a cosine, and then as a sum of a cosine and a sine function. So let's look at this just real quick. This is t, this is our magnitude. Let's just call it v of t for the sake of argument. So what we are told is that our sine wave is 0 and increasing at t is equal to 5.1 milliseconds. So this is arbitrarily going to be 5.1 milliseconds, and our sine function is 0 and increasing there. And our succeeding positive maximum of 11.5 occurs at 9.1 milliseconds. So for the sake of argument, this is 9.1? Yeah. And we had a maximum of 11.5. So that information gives you exactly 1/4 of a sine wave. That is all the information that you need to be able to describe perfectly the rest of the sine wave function, right? Because if you know that this distance is t, the period, over 4, it should be pretty trivial to figure out what the period is, right? The period, t, is exactly 1 divided by the linear frequency, and omega is exactly 2 pi multiplied by the linear frequency. So this time difference gives you omega. The phase angle shift there is going to be this time, let's call it delta t, the amount of shift. So is this sinusoidal function shifted to the right or to the left from a pure sine function with no phase angle? To the right, okay? Because we would expect for a pure sinusoidal function with no phase angle, it would be 0 and increasing at t is equal to 0. Instead, it's happening at a later point in time. So our phase angle is going to be negative, and it's going to be our change in time multiplied by, let's see. So our change in time is measured in seconds, and then omega is measured in radians per second. So when I multiply those two guys together, what do I get? The angle by which it shifted measured in radians. If we want it in degrees, we simply multiply that by 180 over pi. And we have perfectly described every bit of that sinusoidal function just using literally that 1/4 of the sine function we know about. From there, it's trivial to convert the sine function to a cosine function. And as we've already talked about, once we know that, we can convert it into rectangular coordinates and get the components for the cosine with no phase angle plus sine with no phase angle representation. I'm out of time. So I guess the last thing I want to say, all this trig stuff that we're doing today and all that kind of stuff is actually fairly unrepresentative of what we're going to be doing for the remainder of the class. We're not just switching gears and being like, hey, this is a math class now. No, doesn't work that way. Fortunately for some, unfortunately for others. So when we come back on Monday, we're going to actually get into the meat and potatoes of using all these complex number relationships to actually do circuit analysis. And I find it fun. You guys might find it horrifying, but you know, maybe I'm just a jerk. I don't know. So you guys have a great rest of your weekend, and I'll see you on Monday. I promise Monday's videos are a lot shorter.